Good morning, everybody. It's just after 11 o'clock, so we'll get started here. Good morning. Welcome to the February 14th, 2019 version of the Royal Tyrrell Museum Speaker Series. My name is Dan Spivak. I'm the head of the Resource Management Program here at the museum. And today, the Royal Tyrrell Museum and the Cooperating Society are very proud to present Dr. Wynne McLaughlin. Wynne obtained her bachelor's degree in environmental science at University of the Pacific in California. She then moved to the University of Oregon, where she completed her master's degree in 2012, and in 2018 completed her PhD. Currently, Dr. McLaughlin is a visiting assistant professor at Oberlin College in Ohio, where she is teaching undergraduate level paleontology and sedimentary geology courses. Much of the research featured in Wynne's talk today stems from the amazing opportunity she's had to live in Kyrgyzstan for a full year while on a Fulbright researcher grant. While she continues to work on some North American fossil sites, she plans on working in Kyrgyzstan for the rest of her life. Today, Dr. McLaughlin will be discussing the evolution of modern cold-adapted organisms, very fitting for today, and their ecological communities in the Tien Shan Mountains of Kyrgyzstan. So without further delay, I present to you Dr. Wynne McLaughlin.
Thank you. So typically, paleontologists kind of tend to be fairly heavy in the biology side. I'm kind of a weird mashup of part geology, part biology, and how we can combine them to really reconstruct how ecosystems and landscapes change through time. And my dissertation research and kind of everything going forward with most of my career is working in Kyrgyzstan. It's like the coolest place that I'll admit I'd never heard of until my advisor said, "Guess where you're going?" But because today's Valentine's Day, I felt like I had to add in some sort of little nod of the hat to that. So I know you all really are here for the super adorable, only a mother could love face of, this is my most common, a reconstruction of my most common fossil from Kyrgyzstan, a corgi rhino with lovely little tusks sticking out there. Adorable creatures. So why Kyrgyzstan? I mean, I will freely admit I would have not been able to find it on a map until I got offered this PhD project. The kind of big driver that originally brought me there is it turns out Kyrgyzstan has the highest earthquake risk of any country in the entire world. And most people have never heard of that, even most geologists that you talk to, because it was part of the Soviet Union and didn't really have things like seismometers deployed in it until kind of the mid-90s. And then everyone went, ooh, this is sort of bad. And those earthquakes not only directly cause problems because of earthquakes, but they also trigger things like giant landslides. Some of the largest documented landslides in the world are from the Tien Shans of Kyrgyzstan. Now, fossils, as I sort of alluded to, give a great possibility to see what landscapes and ecosystems were like, but also tell how old those rocks are for kind of building back into the earthquake models. The catch being there's almost nothing published. Nothing has really been studied from the entire country. So there's this beautiful fossil record. There's great Paleozoic fossils. There's really cool dinosaurs that I'm not going to talk about at all. And then the ones I really like are these mammals, because the mammals are being recorded, deposited down in these sediments that are happening at the same time the mountains are uplifting, being driven by these huge earthquakes. And some of the fossils are really cool. This would be one of my favorites you'll see some pictures of later, and how I sort of feel about finding them and the really, really gorgeous places I get to work for my research. So Kyrgyzstan, it lies in Central Asia. This is China over here in the Tarim Basin of China. India's here. This is kind of the Himalayan mountains proper, these enormous mountains that result from India being a separate continent and slamming into Asia and kind of crumpling up everything in its path. And it's sort of crumpled and messed up much of Asia so much that the Himalayas have now been uplifted to the point that they kind of can't really go up anymore. But India is still slamming into Asia, and geologically speaking, more recently, we get the deformation resulting in the Pamir Mountains in the Tien Shan Mountains that span Kyrgyzstan into China. And this has sort of set a really interesting stage that relates to us as modern humans. Central Asia, this sort of relatively inhospitable looking climate full of mountains and everything, is where a huge amount of our domestication of both plants and animals have come from. All stone fruits, things like peaches and plums, are from Central Asia. Apples are from Central Asia. And on the animal side, we have quite a bit of evidence that both horses and dogs and sheep and goats were all domesticated in Central Asia. So this has been an area where the landscape has driven the evolution of local plants and animals in ways that have ended up being really important to the sort of development of human society on a global scale. It's also sort of right where the Silk Road came through. It would skirt the edge of the Tarim Basin and have to go through these enormous mountains. And many of the sort of Silk Road stops were along some of these big lakes in Kyrgyzstan. And the Tien Shan Mountains just dominate this entire country. So this is in meters, because I work in Asia and science tends to use metric. But kind of for perspective, I mean, we start at somewhere moderately high elevation and get up to insanely high elevation. So some of the peaks along kind of this margin especially get up into the 25 to 28,000 feet. Really, really big mountains. And I've been working kind of within some of these basins. So the sort of low point in this valley I work in is about 6,500 feet. Pretty darn high. I'm in the sort of 1,000 meters on up. I've definitely had some days where I carried backpacks of rocks down from a field side and was like, man, why am I so beat? And then looked at Google Earth and was like, because I was at 2,500 meters. Maybe that's why. And these mountains, these huge bands of these huge mountains that are being built there, are all bounded by faults. So they're basically this crumple zone. If you've ever had a dog and you throw a dog toy down the hall and they hit the hallway rug and it just goes up in front of them, that's exactly what's happening to Kyrgyzstan, except for the dog in this case would be India. Slightly different. So kind of how do you make these mountains that dominate the entire landscape and shape these ecosystems that we see there today? Here in North America, we tend to think about subduction zones. So if we think of like off the coast of BC, we have oceanic plate, which if you think of oceanic plates are like brownies. They're relatively dense, kind of flat material, versus your continental crust, which would be something like angel food cake. So if you have your brownie and your angel food cake and you're mushing them together, the brownie's going to lose. It's going to go underneath your angel food cake, and that's effectively what we get along the coast. As some of this sort of melts, you get volcanoes erupting, and that's one way you can build mountains, is erupting material. And the kind of traditional other perspective is your continent versus continent, something like this with your two angel food cakes just kind of slowly mashing together. The catch is it's usually way, way more complicated than that. This is a cross-section going from India kind of into northern China, a little bit east of where I'm working. And there's these complicated series of huge thrust faults that form that kind of stack up all of this material. And it leads to all sorts of, not only some kind of melting and you can get some weird volcanoes, but again, this crumple zone where these enormous thrust faults are stacking up kilometer-thick sections of rock on top of each other. And every time one of those faults move, it results in really big earthquakes. So this is kind of, again, the sort of background, the geology-heavy background that drew me into this project. This is what's called a seismic hazard map. So this is mapping the peak ground acceleration, how much the ground surface moves and how quickly when an earthquake happens. And this is one of the biggest factors that controls how much damage there is, but also things like loss of life. And if you look at this global map, you'll see along subduction zones, like our whole west coast here, you get fairly high seismic hazard. But if we zoom in a little bit on Central Asia, it looks even worse. So brown was our absolutely highest seismic hazard risk. And here's Kyrgyzstan, this little country kind of shaped like a frog here. Yikes, that's pretty bad. And it ends up being that as India moves north, we have these kind of bands of rapidly deforming crust. And this is kind of most concentrated currently through the Pamir Mountains and the Tien Shan here. And one of the big questions is sort of when did this start? Is this rate of smushing the same we see today that was happening 10 million years ago? This can make a big impact on the kind of models we build to predict hazard. And this is really important for a country that's rapidly industrializing. So this is the view out of my apartment window when I lived in Kyrgyzstan. It was pretty awesome. I had this incredible view of these huge mountains. But the reason why the mountains are so beautiful and right there is here's the main mountains, here's kind of the foothills, and kind of right behind these Soviet-era cement block buildings is a giant thrust fault with a history of, it looks like, 8 to 8.5 magnitude earthquakes. Really, really big. And I may not be a structural engineer or an architect, but just sort of thinking about it, is this maybe the style of building you really want directly next to your huge faults? No. And a lot of this is sort of, again, unfortunate holdovers of Soviet times, that much of Russia doesn't really have a ton of earthquakes going on. And so a lot of the building strategies and the kind of style of architecture that was developed just wasn't made for this kind of area. There's actually some interesting hypotheses that the prevalence of yurts in Central Asia is in part a response to earthquakes. That if you have a big earthquake, that kind of round structure with the kind of cross bracing around the edges is really pretty sturdy. And worst case scenario, if your yurt falls down, you're not going to die. Whereas if your 8-story cement building pancakes, this is really bad. When also only about 6 million people in the entire country, we have 1.5 million people living in the kind of greater metropolitan area of this capital city right on huge faults. So this is a lot of kind of geology background. I promise we're going to get to some cool fossils once we set the stage just a tiny bit more. So kind of zooming in on, I have the really cool opportunity that I'm the only paleontologist working in Kyrgyzstan. I keep trying to get people to come collaborate with me. Haven't totally succeeded yet. I got an archaeologist to come over, but so I've been kind of concentrating in on, if we zoom in on Kyrgyzstan, this kind of smaller basin that's kind of intermontane, so within the Tien Shan Mountains, is a record of what's happening. And the reason why these basins are so important, especially as a paleontologist, is kind of one of the cool principles of geology. As soon as something goes up, it starts going down as well. If you build mountains, those mountains are also going to be eroding. And all of the dirt eroding off of your mountains rolls down into the nice valley basins, buries the cool dead stuff, and leaves this great record of exactly when the uplift was happening. Our fancy word for that is syntectonic, so within earthquake, basin-filling sequences. The geology nerds really like that one. And it's a pretty spectacular record. So this is one of my field sites in Kyrgyzstan. And these valley bottoms are often really very lush, very green. The rivers are all pretty spectacular colors because they're all glacial melt and just full of glacial flower. And then the sort of normal people would be like, well, here's some boring dry hills. And I'm like, yes, there's dead stuff there. But what's also really neat from this kind of perspective of just how rapidly this landscape is changing are all of these river terraces. So this kind of flat area next to the river is where, when the river's at a high stage, it kind of floods over the bank and deposits out a lot of silt. But all of these subsequent kind of higher flat lines are all old river terraces. These mountains are uplifting so fast that every time a river kind of gets established and starts to cut these new terraces, the mountains uplift even more, and the rivers kind of cut down through, exposing some of the previously deposited sediments. And as these faults kind of continue happening, it also, you can kind of barely see in this picture, these sediments are tipped up on an angle back here, which is really, really convenient for a paleontologist. And then it's like, cool, I don't even have to like dig that deep of a hole to go through time. I can just walk along the kind of dipping layers of sediment. And so these sort of old river terraces have been used to look at how quickly the mountains have been uplifting for about 1 million years. But we need to know past 1 million years. A lot of our earthquakes related to subduction zones happen on relatively short time periods. The 50 to several hundred years kind of reoccurrence intervals that you'll get big earthquakes. Some of our big earthquakes happening over here on these kind of continent-continent sort of plate boundaries happen on the scale of thousands to tens of thousands of years in between them. And the kind of more different earthquakes you can find on a fault and keep track of, the sort of more robust, the better your model is of how frequently these earthquakes happen and how big they are when they happen. So this was sort of the kind of what really brought me in is this is a kind of layer cut through looking at these different age rocks in Kyrgyzstan, and there was a huge amount of argument over how old are they? What do they really tell us? We go from this very old kind of Cretaceous into Eocene, early age of mammals rocks. There's a big gap, and then we get these kind of sandstones and sandstones and mudstones and then huge gravels that are this record of, as soon as the mountains start uplifting, stuff eroding into the valleys. But how old is this base here? In most parts of the world, we would just go find a nice lava flow or an ash deposit and do radiometric dating on it. Kyrgyzstan's been in the middle of a continent since Pangaea formed. Needless to say, that's not super helpful for having volcanoes around to provide a bunch of ash. I thought I found one ash, and then it dissolved in vinegar, and turns out it was actually just like lake sediments. Oops. But I can take this sort of geology context and use fossils to kind of try and calibrate just how old this is by comparing them to some of the other places around the world. So this is some of the previous geology work that had been done at kind of different scales, zooming in on this basin on just how complicated a lot of these faults are as they kind of keep propagating out into the basins and kind of stacking it up, like if you took a bookshelf and tried to squish it into a smaller area. And these red stars represent areas where I found not just a few fossils, but bone beds. These assemblages where there are hundreds and hundreds of bones all kind of stacked up on top of each other. These represent some sort of mass mortality event where lots of animals were dying at the same time. And they're relatively uncommon fossil deposits. Most of our fossils are kind of a little more diffusely spread out through rock strata. And one of the kind of, it's been really fun for me, parts to this is most of these I've found by, I take Google Earth images and say, oh look, there's some light-colored stuff up there. One of my formations that has fossils in it is sort of light-colored. I think I'm gonna go hike around up there, or borrow a horse from my host and like ride a horse over there and hike around in these really incredible mountains and call it work. It's pretty great. So how do I then kind of piece all of this into the story of what's going on? This is one of my favorite flavors of bizarre subfields within paleontology. Taphonomy is the study of everything from when an organism dies to when I dig it up as a fossil. So it tells me the story of what was happening in a landscape, in an environment to cause all of these animals to die, to how have those sediments and bones been turned into fossils and faulted and tilted and changed around. What's sort of the record of what's happened to this landscape during that amount of time? So this is where the fossils really come into play. If you think about kind of different characteristic communities of animals. If I said like the Serengetis of Africa, you'd be like, okay, elephants, giraffes, rhinos, like cool. If I said Alaska, it'd be like caribou, muskox, grizzly bears. We can kind of think about how these groups of different animals relate to the environment that they live in. So you've seen several pictures of what Kyrgyzstan looks like today. It's mountains, it's kind of this grassy steppe land, it's pretty cold, it's very high elevation. It's not what we really would think of as necessarily having some of the animals we see in the past. We'll start out with one, though, that's, okay, horses. Horses are native there. These were pretty close to our modern horses, except for if you kind of look at this beautiful reconstruction, they still sort of have little nubby extra third toes. So instead of just their middle finger, turns out horses are actually flipping you off all the time, they still had these kind of two little side extra toes. And what's really neat is horses are these big animals that are able to move across huge amounts of land really quickly. And from a geologic perspective, almost instantaneous. So horses are one of our made in America greats. And these horses, right at kind of about 12 million years ago, managed to get into Asia via land bridges and then spread out really, really quickly. And they spread out so quickly that they provide this great marker for sort of how old the rocks are. If you find one of these horse fossils, you know you're kind of in younger rocks than that first arrival of these horses. And I have a variety of these kind of three-toed horses. These are both jaws. This is sort of looking down on the tooth surface of a fairly small kind of pony-sized three-toed horse, which Hyperion actually means pony in Greek. It's one of the better scientific names. It's kind of, well, duh. And then this one I really particularly like. It's also an example of why fossil preparators deserve sainthood and are amazing, wonderful people, because when I do horrible things and break the fossils really, really badly, finding them in the field, they glue them back together and make them actually look like a jaw. And part of what made this one both really cool scientifically, but really awful for the poor preparator, was that this is a foal. So this is a jaw of a baby horse. And you can kind of see these gaps where the jaw bone has broken, because these are baby teeth that are just kind of little caps sitting on top. And here are the adult teeth that were getting ready to erupt and come in before this poor baby pony tragically died, but then turned into a really cool fossil. So in addition to kind of horses, one of my other more common fossils are deer. And this is another really neat one. We think about deer here being all over the place. Our deer family includes everything from caribou to moose to kind of your more standard-looking deer. But in terms of mammal evolution, they're actually a really recent invention. They evolved only about 16 million years ago in Asia, and then pretty rapidly spread out and take over huge amounts of the globe. They do things like outcompete a lot of the horses that had been much more common fossils through huge amounts of time. And some of the first sort of attempts at deer being deer are really weird. It takes them a while to figure out having relatively normal-looking antlers. So these deer I have in Kyrgyzstan look pretty darn modern, as opposed to, if you look at some of these slightly older ones, there's this great weird group of deer that I wish got more public attention that are called crown of thorn deer. So if you think of the kind of traditional religious art of Jesus and crown of thorns, that's what their antlers looked like, is these crazy spikes erupting out all over their head. Pretty crazy. And even my deer in Kyrgyzstan would have looked a little bit odd, and that instead of that antler coming right to the base of their skull, they actually have their skull kind of projecting out a little bit, and then the base of the antler. So when they shed that antler, they would have still had kind of weird knobby spikes sticking out of their head. A little strange, but they're relatively close. And I get, this is some of the only material that fossil material had been collected before I got there. Some geologists picked this up, and you can see kind of some deer teeth and antlers, and then I have several different jaws, as well as a bunch of antlers, and even a whole foot that is one of my favorite fossils. The catch is, I'm starting to play around and working on deer. There's like one guy in Romania that works on fossil deer, and I sent him some pictures and was like, "You work on deer, please help me." And he was like, "Yeah, those are deer. They're older than what I work on. Don't know." Like, so who can help me? It's like, good luck. So if you have any friends who have a great desire to work on fossil deer, send them my way, because, I need help. I have lots and lots of deer fossils, and no idea really what it is. It's been a challenging thing. We can kind of say they're modern-like deer, but their family tree, their taxonomy of how they've been named and kind of arranged in this family tree is, let's just not talk about that. Next. On even weirder things, though, so deer and horses, you're like, okay, I can imagine that in Kyrgyzstan. How about giraffes? Kyrgyzstan used to have a diversity of weird giraffes across actually all of Eurasia. There was this fairly big giraffe. This guy's about 2.5 meters tall at the shoulder, so quite big giraffe. And not quite as long a neck as modern giraffes, but this kind of similar body proportions. And I have quite a few teeth as well as some neat leg bones of this fossil giraffe called Samotherium. Now, thinking about how animals interact with each other is something else I kind of like to play in with paleontology. And your homework for tonight is, if you have never watched a video of modern giraffes fighting, you should go watch a video and then think back to this fossil giraffe having almost meter-long spikes sticking off the top of its head. The few of you who've seen giraffe fights, you're already like, "Ooh, no." And it gets a little weirder. There's also this other entirely extinct group of mammals that are like if you horribly mash together a deer, a camel, and a giraffe into one animal, and they're supposed to be extinct by kind of 10 million years ago in Eurasia, except for I found this partial skull. So this is looking up at the roof of the mouth and these complete rows of teeth on either side. And I talked to all the people who work on giraffes and the handful of people who work on deer and everything else I could kind of try and make it into, and they're all like, "Nope, that's a paleomericid, this weird thing here." So unfortunately for me having to do a bunch more work, this is a new species and genus, and I'm hoping to name it Kyrgyzmeryx, which will make it like one of the weirder spelled names ever. But sort of, I know, it's fine. Meryx means sort of deer-like, and so it's a kind of frequent ending used to describe some of these animals. Paleontologists get to come up with horrible names. We're sort of bad about it. On the sort of everyone likes fierce creatures, our carnivores running around in this ecosystem seem to be mostly hyenas. And we have two great flavors of hyenas in these Kyrgyz sites. There's a sort of smaller one, which by smaller I mean wolf-sized, still a pretty darn big animal. And for those of you that have dogs, these are sort of way more robust and sturdy teeth than you would get in a dog, even a wolf of the same size. So these are bone-crushing hyenas. These are the cleanup crew that's running around chomping on all of the dead horses that are lying about. And it actually gets a bit worse. My last field work in 2017, going back this summer, we found this beautiful jaw. This is it in situ, so when I found it in the field, still embedded in the rock. This is a pretty much complete jaw by the time we dug it out of Adcrocuta eximia. This is a grizzly bear-sized hyena that when people look at biomechanics or sort of modeling the physical mechanical properties of fossil animals, probably had a bite force about twice that of a grizzly bear. So let's take a grizzly bear and make it even worse and then give it pointier teeth and turn it loose in Asia. For the reasons of, people ask me if I had a time machine when I go back to the time period I study, this is one of the really big probably nots. And one thing that's kind of cool too is that we'll get into what this really means. For every single little bit of carnivore, things like these hyenas I find, I have hundreds of specimens of plant eaters. Now, the sort of food web is reflected a little bit, but this is kind of an extreme case. Carnivores are really, really rare, extremely rare, and these beautiful bone beds I'm getting out of Kyrgyzstan. And the single most common thing I have, though, by a huge margin, are rhinos. This is another one that you think Central Asia, mountains. We don't think rhinos. We mostly think of rhinos now as like an African animal. They're also in India. There's the almost extinct Javan rhino, but like kind of tropically warm places, not running around at high elevations. But what's really neat about this group of extinct Chilothere or Chilotherium rhinos is that these are thought to be the ancestors of woolly rhinos. So our Ice Age Arctic rhinos that we did get this far into Canada, huge, woolly, giant horn, had these sort of derpy, corgi-like early relatives. And I keep calling them corgi-like because even compared to modern rhinos, these guys had rounder, barrel-shaped bodies and even shorter, stubbier legs. And I have tons and tons of bones. I mean, probably literal metric tons of bones, as well as just sheer number. So this is a arm bone, this is an ankle bone, and here's a much more artistically talented reconstruction by my friend Liz White of what these rhinos looked like. And while the horns themselves are made out of the same material as your fingernails and therefore don't fossilize, they leave kind of a rough part on the nasal bones so we can tell where those horns attached. And these guys didn't have any of the horns, but they did have these two kind of silly tusks sticking out the front of their face. And this is sort of one of my cooler fossils I've found. We were so excited to find a almost entirely complete skull. So this is missing just a little bit at the very front of the skull where the front teeth would have been. But so here's its nose bones. It has kind of a funny nose that sort of sticks up very far, and the sort of entry to the sinuses comes back very far, which our only modern things we really see this in are tapers. So adding to the kind of how special this rhino might have looked, we already have our corgi-like body proportions, our lack of a horn, our big tusks in the lower jaw, and they might have kind of had a trunk. So this is, again, back to the like face only a mother could love, but this is my baby. This is my special fossil. I think it's beautiful. And this particular rhino represents a new species that I'm working on describing as well. And here's some of its teeth, kind of back of the skull, little beady eyes in there. You know, rhinos have it pretty hard. They have very poor eyesight. They don't have a lot of space for their brain to actually fit in their skull. And to make you even a little bit sadder, because all modern rhinos are threatened with extinction, all modern rhinos and most of our fossil rhinos are also riddled with arthritis. Turns out arthritis doesn't kill you, and it doesn't impact your ability to have babies. So there's no selection against having arthritis. And rhinos' closest relatives are horses. So how they move, their gaits that they use to move, are from that common ancestor they share with horses. So, you know, we have any horse fans out here? I mean, it's close to Calgary. Horses have walk, trot, canter, gallop. Rhinos do the exact same movements. Almost all other really big animals like hippos or elephants kind of do this great shuffle. They leave 3 of their feet on the ground at all times to support their weight. Rhinos gallop, so they pull all of their legs off the ground at once and slam them down onto one of their back feet, roll through and push off one front foot. It's a huge amount of stress from their very big bodies and results in them having some pretty bad bone pathologies. Sorry, rhinos. But for reasons why I love them, and I think they're really cool, this is a map just looking at our Miocene. So this is sort of 20 million years ago to 5-ish million years ago. We have rhinos pretty much all over the world. We get them all over North America, Europe, Asia, and there's not been a lot of work done in Central Asia. So I'm kind of trying to add in some of this story of where does this family come from? And how did they go back and forth? Horses evolved in North America, so did rhinos. But they get back and forth several different times. So another sort of avenue of my research I have so many rhino fossils from Kyrgyzstan, they're all new species, unfortunately, for me, is I'm working on kind of redoing the rhino family tree. So this is what's called a phylogeny. So this is the kind of stats behind how different parts of the rhino family are related. And we have our modern rhinos kind of falling out over here. And I don't have them in this one, but woolly rhinos would come out over here. And so these Kyrgyz rhinos are kind of a little bit down on this tree, leading to our woolly rhinos, but a pretty separate branch from the rhinos we see today. And again, my sort of Valentine's factoid is another thing that I think is really cool with these special rhinos is they're actually sexually dimorphic. So sexual dimorphism is when males and females are different. And they vary a little bit in overall body size, which can be hard to tell in the fossil record sometimes. But some of our sites, like in Kyrgyzstan or in China, where we have lots and lots and lots of these fossils, it turns out they're different in their shape and length of those adorable lower jaw tusks. Males have longer tusks that are also kind of flatter. They're more oval in cross-section, possibly because they may have been using them to fight each other or have some sort of competition. Whereas the ladies have these shorter tusks that are kind of round in cross-section. So what I find really fun about that is that beautiful, mostly complete skull and complete jaws I have with it are a girl. So we have brought in our sex for Valentine's Day in terms of biological sex. It's everyone's ideal Valentine, right? This is why I'm a paleontologist, not an artist, too, but I tried. And kind of how does this all piece together? So I've introduced all of these crazy, weird animals, or some not so weird, but how do they kind of relate to what's going on in an ecosystem? We have some things that you could believe would be in Central Asia today, but we also have a bunch of animals that really seem more like what we think of for Africa today. Things like giraffes and rhinos. So looking at this kind of proportion of different types of animals at individual sites can kind of start to tell you a bit about what's going on in the environment. If we have, in this case, lots of these large-bodied herbivores, there has to be something for them to eat. And we can take it a step further and look at kind of how their teeth are shaped and how their teeth are worn to assess a little bit about, are they grazing on grasses, which often grinds your teeth really flat, or are they kind of eating leaves and sticks and things like that, which you sort of have to mash together and tend to leave this more jagged wear on the teeth. Uniformly, even in things we usually think of grazing and eating grass like horses, we get this sort of rougher wear, implying these animals were living in an environment that was sort of shrubby to tree-filled, and eating a bit more diverse plant matter, not like what you would see today in Kyrgyzstan. And this is sort of zooming in on one of the sites. This is one of those horse jaws that was pictured earlier, and also kind of shows some of the challenges of excavating a lot of this stuff. So this is a tibia, your shin bone, from one of the rhinos with this horse jaw just sort of mashed right onto the top of it. And of course, they're all riddled with cracks. And then there's these really obnoxious plant roots growing through everything. You get told, drink milk, it'll make your bones strong and have calcium in it. Calcium is a mineral and therefore preserves in the fossils really well, even after a lot of the biological material has been replaced. This sucks to paleontologists because it means that plants, will exploit your fossils to try and get nutrients out of them. So I don't want any of the nasty plants getting in my fossils. Sorry for plant aficionados, but I can kind of look at sort of some of this. This surface here was broken before this was fossilized, implying that some transport, some sort of movement or scattering of bones happened before this was fossilized. And kind of compare, do we have whole skeletons? Do we have whole limbs? Do we have kind of what degree of complete elements? And finally, I look at a lot of how weathered these bones are. So this tells me this kind of story of how did these animals die? What happened to them after they died? If we have most things being relatively complete, I have a lot of partially articulated skeletons, like complete legs, even with tiny little toe bones. We get a big sort of mix of different things, and none of these bones show basically any weathering. So these are animals that died pretty quickly. They weren't sort of lying out, decomposing, and were buried after dying over a short period of time. So kind of thinking about, okay, what sort of modern situations can we do that in? Some of our other little pieces of information we can add, and this is the complete jaw while it was still in the rock, back of the jaw, the teeth along here and the tusks there. I can look at sort of things like, what's my percentage of juvenile, baby animals to adults? Now, what's pretty cool about this is this sort of mass death, when animals die suddenly all at once in some catastrophic event, is one of the only times you preserve baby animals. The sort of sad truth of baby animals is that they're delicious, and so everything eats them and processes those kind of tender young bones. Baby animals are pretty rare in the fossil record. I have a really lot of baby animals. Some of my sites are in this sort of high end of what's seen in even modern communities when you have things like huge droughts in Africa, where almost a third of the fossils are from baby animals, like that foal jaw, as well as I even have a fetal rhino skull, partial skull. So kind of piecing all of this together, the sort of modern way that we see kind of the most similarities of these bones that are unweathered and haven't been transported very far and represent a bunch of stuff dying all at once with a whole bunch of baby animals are huge droughts in Africa. So my kind of hypothesis for how this relates back to what's going on with our ecosystem is we know Kyrgyzstan didn't used to be as high elevation, didn't used to be as mountainous. And we have these animals that were eating trees, bushes, things like that. How do we shift that to this open environment? Well, a great way you can do that from a geologic perspective is this mountain building. So India's climate currently is characterized by monsoons. Those monsoons used to reach Central Asia, and there's been a lot of debate about exactly when they stopped being able to make it to Central Asia. And I'm proposing these kind of same ages that I see these mass deaths of my poor rhinos are when these mountains finally uplifted far enough to block the monsoons from reaching Central Asia. And you start getting these huge droughts changing your ecosystems and unfortunately killing off many of your rhinos. So that's kind of my environmental story, but the catch is, when did this happen? We need those dates to kind of feed back into these earthquake models. So trying to figure out exactly how old this is and what's going on is kind of my other side of my research. I would way rather wander around and dig up fossils, but I also end up wandering around collecting rocks. And what I'm using the rocks for is, again, we don't have anything we can do this radiometric dating on, but the magnetic poles in the Earth, so north being kind of up as we think of it, have actually changed a whole bunch during Earth's history. And conveniently for a geologist, they don't change consistently. You'll have sort of north up for 1 million years and north down for 200,000 years, and it flip-flops back and forth, making this sort of barcode. So measuring through these kind of layers of rock, if you think of them like your cake stratigraphy again, I can take individual samples and measure what way north was to reconstruct at the time those rocks were being deposited, north being kind of normal are these black bars, and north being actually in the south are these kind of white bars. Now the catch is, this is a barcode. You can imagine you could take a barcode and kind of match and correlate that almost any way. Most of the previous work coming out of Central Asia, that's what they've done. It's been like, well, it kind of works this way, so let's say This particular layer in a recently published paper is 35 million years old. Well, the catch is I have fossils from that layer. And included in that are things like this horse that doesn't make it to Asia, to the entire continent, until a little bit less than 12 million years ago. Also things like gazelle fossils that, again, don't show up in the entire continent until about 11 or 12 million years ago. And we can tell this from areas like China, where we have both those nice volcanic ashes that tell us exactly how old the rocks are, and the fossils, like what I really wish I had in Kyrgyzstan. So I take kind of all the different animals that are in each of these bone beds and look at their global records of how long ago did these animals live. How well do we know kind of the time range they were around for? Some of them have fairly long time ranges, like gazelles. But my corgi rhinos here are really only around from this kind of same sort of 12-ish million years ago to 5.5 million years. And then they go extinct and are replaced by kind of our proto woolly rhinos. And this modern deer, this modern style deer at least, are also really important in that I said they're sort of evolutionarily recent inventions. And we don't get deer with antlers that kind of have that antler base until 9 million years ago. So for this particular site, I can say, okay, the fossils tell me it's somewhere within this range. Yes, that's a couple million year range. That's not perfect. We would love to have better. But it's a really lot better than the previous work that's like, dartboard, let's call this exact site 35 million years old. I can say that's wrong by a lot. And I do this for kind of each of these bone beds. At kind of the more fossils I find, the more different species I'm able to identify, often the kind of better time resolution I can get. Here I get things like, again, the rhino, but also this hyena showing up for kind of a shorter period of time. So even though this hyena itself has a longer range, I can kind of couple together these different fossils you see to, in this case, I'm starting to get pretty decent. I have 5.5 to kind of 7.3 million years as a possible range for one of these sites here. And one of the kind of fun ones I really like, that is another who knew they would have been so useful, are bunnies. One of my sites has rabbit fossils. We don't get modern rabbits, as we think of with like hopping, until 7 million years ago. And I have a almost complete rabbit skeleton with kind of 2 hind limbs, 1 front limb, a jaw, and a little bit of a skull that we had a lot of fun kind of joking about because we'd found a partial rhino skeleton and we're digging out the rhino skeleton, and then right under sort of the back end region of the rhino, we dig it out and there's a bunny fossil. So, might have been the bad cause of death for the bunny, but I'm really glad it ended up in my fossil record. So each of these assemblages of fossils gives me these age estimates that then I can combine with these barcodes. So this is sort of a global known barcode for how our magnetic poles have changed over Earth's history. And for each one of these sort of layers that I have a fossil in, I can say, okay, well, it has to fit, this little barcode has to fit somewhere between 5.5 and sort of 7 million years for this layer right here. There's only so many ways that it really forms that great of a match. And in some cases, like the site with the rhino skull, there's really only kind of one reasonable way that it matches particularly well. So all of a sudden I've gone from a couple million year resolution to potentially more like 100,000 year sort of age resolution on some of these sites. And this is really important then for feeding back into those models of when the Tien Shan Mountains started uplifting along these huge earthquake faults and depositing these sediments. So if we have this sort of 11 to 12 million years ago for the base of these formations that are filling the basin as the mountains are going up, all of a sudden that makes a really big difference for these earthquake models, as opposed to having 35 million years of time to build these mountains. So we're really, really rapidly building these sort of baby mountain ranges that are, again, causing some serious hazards. So kind of my take-home messages from this is this kind of all pieces together with how these landscapes and environments change to suggest that the Tien Shan Mountains are really, really young and just absolutely shooting upwards, which from a geology perspective, doing science, you're like, wow, cool, baby mountains. From this kind of global hazard perspective, it's scary. It implies that these really, really big earthquakes we see today are kind of the norm. And that this is how you build these mountains, are relatively frequent, huge earthquakes that could do some pretty bad things. And this building of these mountains so quickly shifts these ecosystems over a fairly short period of time from being kind of nice, happy, kind of semi-wooded open areas to mountains with stepplands. And this sort of forces faunas, the animals living there and the plants as well, to either evolve or die. So you either have to go extinct or you have to become adapted to things like high elevation and cold. So my rhinos being sort of this ancestor of our woolly rhinos, our cold-adapted Ice Age faunas, this is sort of the trial by fire, or trial by uplift, really, in this case, is you evolve or die. And kind of putting this in graphics, again, here's our sort of India. These are GPS points showing, even within a year, some of these places, how much faulting and how much movement you're getting. This is not a slow process. I mean, in some places, we're getting a centimeter of shortening in a year. That's a huge amount of time if you think about this is mostly being accommodated in earthquakes, where you might have a rupture that moves 5 meters in a single event. And this is what it really takes to very quickly go from an environment that looked something like this, with kind of some trees and brushes and kind of low foothills and our happy rhinos running around with our ponies and whatnot, to this kind of Ice Age to modern ecosystem we see today. That's high elevation, we have a lot less trees and open area, and we've really changed kind of the environment and the food sources available. And this has continuing implications for what's going on in Kyrgyzstan today. Not only things like earthquakes, so these are models of how much damage would happen if there was an earthquake right here next to the capital city. The difference between these two models is how old that uplift is. This is if the uplift is much older. This is actually, unfortunately, what my research suggests it is. These way higher hazard scenarios. Kind of scary. And from a sort of evolution of these cold-adapted fauna, this is pretty important, both in that today, here's our modern range of snow leopards. Here's Kyrgyzstan. It's like entirely snow leopardville and has one of the highest remaining populations of snow leopards. And also has, kind of from really nearby, the oldest known fossil snow leopards. So again, this kind of rapid mountain building, rapid climate change driving the evolution of what we think of as cool mountain faunas today. And this climate change is continuing. So this is a glacier I visited several times in Kyrgyzstan that honestly is now way back up here. It's rapidly retreating. And we kind of think about this as kind of an abstract thing, but in Kyrgyzstan this matters a lot. About 40% of the population in Kyrgyzstan depends on small glaciers to have a water source for most of the year. So as these smaller glaciers completely disappear, entire villages are being forced to pack up and move because there's no water huge amounts of the year. Kind of a little doom and gloom to finish it, but on that sort of light note, thank you so much for coming and hearing my talk, and I have both the Fulbright as well as a couple other sources of funding. If you want to see lots of pictures of mostly really broken fossils, but that I'm trying to glue back together, I'm on Twitter and I post a lot for Fossil Friday. And Kyrgyzstan's really cool. I'm happy to take sort of questions on everything from living abroad to weird corgi rhinos.